Okay. Homework. Anybody doing anything on homework?
Yes, I'm attempting.
Okay. Which one?
I've attempted one and gotten pretty much as far as I could on that one. As to, then I started on the second one, but.
Okay. Okay, the last time I'd gotten all the way to the end of number 2. And there's only one other problem that is solely about finite difference. Okay. I was supposed to put some code out for you guys, and I totally forgot to do that. So the code that's referred to in the hints. So, well, actually, yeah, tomorrow in 465.60, I'm going to teach about numerical differentiation formulas. So you've been seeing that in this class already, but now you're going to see it even more. So the goal is to make you sick of it. Yeah, and so I have some code that whose job it is that you indicate which points you want to use for a finite difference approximation. Like, if you want a derivative at x naught, do you want to use points like x naught plus h, 2h, 3h, or maybe points on either side, like plus and minus h, plus or minus 2h. So really it's the multiples of h that you indicate. So if you want a center difference, you use minus 1, 0, and 1. If you want a center difference of 5 points, it'd be minus 2, minus 1, 0, 1, and 2. And it'll give you the coefficients. So that saves you from doing a lot of work on paper. Well, okay. I definitely want to make sure I talk about problem 3.
Can I ask a question real quick about 2?
Yeah.
When you were talking about creating our matrix of A and then like the B portion of that, and you said it needs to be n by 3, does it matter what our n is? Is that?
Okay. Well, first of all, the comment I made about n by 3 is like how a sparse matrix is internally represented. But yeah, you're just going to use SP diags to actually create it. Now, so you're asking about like the actual value of n?
The dimensions, is that like the?
Okay, I remember making a remark about like just choosing something, and like just maybe like powers of 2 or something, and you just need to choose a few of them, like maybe pick a value and keep doubling it, so that you have a few different errors, so that you can check, well, is the error going to 0 at the correct rate? But yeah, other than I don't really care what values you pick.
Okay.
Shouldn't little m and little n equal big N? If they're the size of A and A is just m or n by n.
Wait a minute. Like what I wrote in the notes.
Because you do SP diags.
When I described the general usage.
Yeah.
I had like B, D, M, N. Yeah. So in this case, for this problem, little m and little n would both equal big N. Yeah. All right. Okay. Might as well take any other number 2 questions if anybody has them.
I didn't know these were MIT problems.
See, I ain't watering stuff down.
No.
And what I said earlier, yeah, play the game at the highest level. Yes, you guys are doing that. Okay, we don't cover as much as that MIT course, but it cuts off at an earlier point. But what we do thoroughly. Right. So no other number 2 questions at this point. Okay, well, there probably hasn't been much opportunity to write actual code, try that out yet, but hopefully between now and Monday, course, I'm aware of several other things you all have going on, so, etc. Okay, and number 3 is fairly similar. It's another finite difference thing. Okay. This deals with a different PDE, and it seems we're always bringing up Poisson's equation. Which is something a little different. The biharmonic equation, 4th order PDE, so mu xxxx is equal to f. One kind of problem where 4th derivative with respect to x comes up is structural analysis. There's a PDE called the beam equation. 2nd derivative with respect to time and 4th derivative with respect to x. So it's modeling like the displacement of a beam when under whatever load is placed on it. So you can tell if your building is going to collapse or not. I'm pretty sure I've never, ever seen a PDE with a derivative of order higher than 4. And even 4 is pretty rare. So that'd be interesting to have a PDE that's like 5th derivative. So I'll just look that up and see if there's something out there. Well, figure like what do derivatives mean? Like first derivative, like if it's with respect to time, you have velocity, and 2nd derivative is acceleration. Does anyone know a term for the 3rd derivative with respect to time? There's actually a term for that from physics.
Wait, which one?
3rd derivative.
Jerk.
Yes, jerk.
Pop is the 6th derivative.
Pop?
It's called pop. Physics.
Freaky.
So like the 3rd is jerk. It goes velocity, acceleration, jerk, snap, crackle, pop.
Oh, they gotta be punking
I
us.
swear to God. Well, this is Wikipedia, so maybe some jerk went on
Yeah.
that.
Okay. Well, if multiple reputable sources,
They do have references. It literally it goes acceleration, jerk, snap, crackle, pop. But I don't know what.
is there any explanation? Because for jerk, there's an explanation like basically a jolt that happens.
It says pop is the rate of change of the crackle.
Oh, but they're just making that up.
And pop is defined by any of the following expressions, which are it's just the 6th derivative.
And someone just wanted to, if you
Part of me wants
could
it
find a
to be
physical
true,
meaning
though.
for it. What?
I want it to be true, though.
Oh, yeah, I do too.
I know, 'cause that's just
Let's just leave it there.
There's the initial pop and the final pop and the constant pop.
Okay.
That sounds like someone above the base of
I wanna
talking about.
Jeez. Okay. Well,
That's not
all right. Jeez. Okay. Anyhow, so because this is all right, so same kind of domain, 0 to 1, because why not? Now, because it is a 4th order PDE, we need 4 boundary conditions instead of 2. But there's similar kind of, so U0 and U1 are 0, like before, Poisson's equation. And we also have the first derivatives. At the boundary will be 0. Okay. And for this problem, f is set to be a constant, 24. Okay. Now for error analysis, you need an exact solution, like in the previous problem. So you're going to do the same thing as at the end of problem 2. You're going to integrate the constant 24 4 times. To find a function u whose 4th derivative is 24, so you're going to get some 4th degree polynomial. But you're also going to get 4 plus c's. And the way you're going to figure what those should be, make sure they satisfy the boundary conditions. Actually, the nice thing is the boundary conditions at x equals 0 will cause a couple terms to just drop out altogether. So that helps. Yeah, so you're finding a 4-degree polynomial that satisfies all that. Okay. Okay. So the plus c's satisfy the bc's. Okay. So that's the first thing you do. The second thing you need to do is get a 5-point stencil for uxxxx. So the idea is, and yes, I'm supposed to put some code out there. I feel like that would be making it too easy because you can just run my code and bam, that's the answer. But I do want you guys to understand how this comes about. And I did cover this. So the idea is, it's a linear combination of five values of u.
Say, is there a subscript -2 on C, or is that just 2?
That's a -2. I'm making the subscript match the multiple of h.
Oh.
Then we go all the way up to +2. Okay. So 4-2 will be a linear combination of these 5 values of u. Now, if you were to Taylor expand these, and go through a procedure that is described at the beginning of chapter 2, you end up solving this system of equations. So your unknowns would be your coefficients. Whoops, don't leave minuses there, we're in the wrong place. Okay. So what you have here is down the middle column, it corresponds to u of x naught. The rest of that column would be all zeros. Then in this column, you would have so this column corresponds to the coefficient of u of x naught plus h. So I'd have h squared, h cubed, h to the 4th. Okay. And then I'd have 2h squared, and so forth. All right, and then I'd have minus h raised to powers, and then you can figure it out from there. Minus 2h raised to powers. Okay. And then the right-hand side, so you're trying to approximate the 4th derivative. Each row corresponds to a value of u prime, u double prime, u triple prime, when you expand all this. But you want those derivatives to not appear in the result. So you want the terms involving u prime, u double prime, everything before u fourth to be 0. So that's why all these are 0. And then this last right-hand side value would be 4 factorial, because in a Taylor series expansion, the fourth derivative terms already have a 4 factorial in the denominator that you want this to cancel out. So now, this whole system was derived earlier in chapter 2, so I would refer you to that to see, refresh your memories to where all this comes from. I was saying, okay, this is a system that has to be solved. Okay. Now, if you want to do this in MATLAB, the problem is you couldn't put in the system directly because there's a variable in it. There's these h's. And in MATLAB, you're inputting a matrix of constants. And I'm not even going to get into that whole symbolic package crap. Or symbolic toolbox. Not needed. So here's what you could do instead. You could go ahead and set up this system and solve it where you let h equal to 1. So then you would get the coefficients that correspond to the case h equal 1. And then in your formula, your actual formula for a derivative, this will give you the coefficients that go in the numerator, and then you divide by h to the 4th, because it's a 4th derivative. So whatever derivative you're trying to approximate, that power of h goes in the denominator. So really, you don't need that code that I forgot to post. Well, I'll put it out there anyway, but well, you can have MATLAB solve this for you. Everybody else run my code and make sure it's right. Or you can try Googling the formula of 4th derivative stencil, and you probably find it. And it may even be in my book. I have no idea.
I missed it. Is that 4 factorial or just very excited for? Serious.
I'm going to use that. It really is a 4 factorial because of a 4 factorial in Taylor's theorem. But that's one of the things I don't like about factorial, because there have been a lot of times, and you may have witnessed them, where I'm going through some derivation step after step after step to show that something is equal to 0, because that's the result we always like to get, because we just want these stupid expressions to go away. And when I'm doing this, I sometimes can get excited, like, and it equals 0, because it's some shocking conclusion. And I want to write 0 with an exclamation point, but it makes it 1. So, yeah. So that is taken away from me. I cannot express my excitement on the board. So, yeah. Yeah. What? I'm sorry. What?
We need to create a mathematical
Oh,
symbol.
yeah. For an excited.
For excitement.
For. Yeah, but now remember what my advisor was like. Maybe I got this from him, because, as he was working something on the board, I remember, just the way his voice was sound, like, and reached that conclusion, and then he'd settle down. Yeah, his classes always went like that. So, Then again, there's no professor I've ever known who gets more excited about things like this than Dr. Ding. I mean, yeah, who I still hear in his class during our meeting. Yeah, so, right in this room. No, I should. I probably could get excited in class, but then I feel like look at me like, what the hell is he on? So, okay. All right. Okay. Yeah, we're not getting squat done today. Okay. So, but yes, we are. We will. There's not much more to say about this problem, so we're good. All right. So you have. So that's how you get your 5-point stencil, and then so that's the second major step of this problem, and then for the third step, like in the previous problem, really anytime solving a time-independent PDE, you're setting up a system of equations to solve. And your matrix A will be 1 over h to the 4th. And since it's a 5-point stencil, so these coefficients that you get from your system, like whatever C0 is, will go down a diagonal, and then C1 above, C2 above that. So it's a pentadiagonal system. In other words, there's 5 non-zero diagonals. So you can use SP diags again. Bless you. So you have 5 diagonals to fill in instead of 3. Okay. And I feel like I'm missing something here. Okay. So the thing to talk about are the boundaries, because this is an issue with problem 2, where you also had a 5-point stencil for second derivative. And everything other than the first and last rows, no issue. Because, like, in the interior, you have 5 coefficients multiplied by 5 of your unknowns. So that's okay. The second row, or second last row, also not a problem, because you're using one value that's outside your domain, like it's on the boundary, but that value is 0. So again, non-issue. As far as this is concerned, so let's talk about the left boundary. You're approximating u x x x x at x naught. And kind of surprised we don't discuss this in the hints file, but maybe, and I don't remember what happened, but maybe when I write it out, it'll turn out to be moot. So what the approximation would look like is over h to the 4th, I'd have c minus 2 u of minus 2h. X1. The first equation corresponds to 4th derivative at x1. So that would be x1 minus 2h. But x1 is the first interior point with spacing h. So x1 is h, because x0 is 0. So really what goes in here is u at h minus 2h, but really that is minus h. Okay. And then c minus 1, u of 0, plus c0 u of x1, which is one of our unknowns. Actually, I'm going to just call this u1. Again, because it's one of our unknowns. So then c1, u2, to u3. So these coefficients are multiplying u1, u2, u3, because that's what goes in your vector of unknowns. Okay. Questions about what I just wrote here? Okay. All right, so these. So we have to deal with these terms because they're not among our unknowns. Now, the first term, or not the first one, this term. Oh, I'll wait.
Just the last 3 are unknowns.
Yeah, so we definitely don't have to worry about those. Okay. Why is this one not a problem?
It's just 0.
Yeah, it's a boundary condition. So that's gone. But now this term remains. And what are we going to do about that? So, just need to erase that by hand, but okay. But yeah, it is gone. Okay, so we've used, oops. We've made use of this boundary condition, but at x equals 0, we also have this boundary condition, but not used. Okay, so u prime is 0. So what we could do with that is, so ux of 0 equals 0. What we could do is use a center difference approximation. So u1, which is u of h, I could do this, minus u of minus h over 2h equals 0. Now, u of h is u1. That's one of our unknowns. So I'll just fill that in there. Okay. Now, what this is saying, though, is that this u of minus h that's over here is equal to u1 from this equation. Because that derivative is 0. So from this, we get u of minus h equals u1. Okay. So I can fill in.
So UH and U minus H are the same?
What? Sorry, what?
UH and U minus H are the same?
Yes. Because of this condition. Yeah. Yeah, so this often happens where you have this is a Neumann boundary condition, derivative being 0. Well, what does that mean, derivative being 0? The function's not changing. So values on either side of the boundary are equal. Okay, so what that means is u1 appears in two terms. c1 multiplied by c1 here, multiplied by c minus 2 here. So,
U1 does?
yes, because
I thought
that's,
that's U2
what?
with C1.
Oh, yeah, that's what I meant.
Okay.
Yeah, so, yeah, I looked at the wrong one. Literally, 1. U1 is involved in two terms. So what that means is, well, but whatever is multiplying U1 has to go in this spot in the matrix. So I add on C minus 2. So that coefficient gets lumped in there. Okay. And same thing down here, of the opposite side. I'll add on C2.
What would be negative? Would they both be negative?
No, because this concerns what's happening at the left boundary, u of x naught minus 2h. Whereas here, we're at the opposite boundary, and it's u of x plus 2h that is outside.
And that doesn't correspond with U3?
Um,
Since you're multiplying C2.
Well, okay, so what will happen in this case is, okay, on the right boundary, it's these terms, the first three, that correspond to unknowns, and the last two that are sitting outside. So it makes everything backwards. So if you carried out what I just did here, only for the right boundary, I'd have c minus 2, c minus 1, c0 multiplying interior stuff. And then c2 would be multiplying u n plus 2. And then down here I'd have this would be un, and this would be u of 1 plus h. as opposed to 0 minus h. Yeah. So that's why instead of adding on the first coefficient, the leftmost coefficient, I'll add on the rightmost coefficient. So leftmost coefficient for left boundary, rightmost coefficient for right boundary. Actually, I think the value of those coefficients will be the same. Okay. Yeah, so these are things that had to be done to handle Neumann boundary conditions. When I first covered finite difference, I think the first or second day that I did it, I had a problem where I had a Dirichlet condition on the left side and a Neumann condition on the Dirichlet condition on the left side, Neumann condition on the right side, and I had to do some funky manipulations to handle the Neumann condition on the right side. And it turned out what I did is exactly like this. It's the same procedure to eliminate something that is not among your unknowns in the first place. So it ends up changing a diagonal entry. Fortunately, this matrix remained symmetric. Like the stencil you'll get when you solve this system will be symmetric. Like these coefficients will be equal. These coefficients will be equal. So since we're only changing the diagonal entries, you'll still have symmetry in the matrix. However, the matrix will no longer be toplets. Who remembers what toplets means?
Zero.
No,
Everything else is zero.
not zero.
About that one, the error that it has.
Sorry, what? Okay.
Oh, it's all the diagonals are the same.
Yes, because now this diagonal will have different entries on the first and last. So, so that's unfortunate, but okay. Okay. Your f won't be a problem. That's just a vector of all 24s. For your right-hand side. It's because there are no non-zero boundary terms to worry about. But yeah, because all the boundaries are set equal to 0. If we did have non-zero boundary conditions, there would be something added on there. Okay. Okay. So once you set up this system and solve it, just you analyze the error in exactly the same way as problem 2. So because you'll have an exact solution, so you can measure error that way. You try this out for a few different grid sizes, like in problem 2. Plot the error versus h, and it should be second order accurate. So this finite difference stencil for a fourth derivative is second order accurate. Here I used a centered difference for the boundary condition, also second order accurate, so that should make everything second order. Okay. Questions about any of this? Okay. Right. Well, we've not run out of time yet. Problem 4 is the first one that gets into spectral methods, except there's 2 parts to it. First one, you do a finite difference again. And then the second part is where you solve the same problem using a spectral method and compare. Okay. Actually, yeah, certain elements are exactly the same as before, but there's some new wrinkles too. Actually, in a way, the spectral methods part of this is easier. Because you're given, the matrix is given in the notes. And I tell you in the hints what you do with that matrix for setting up a system. So I may not even really need to talk about that until you guys get around to it. Okay. Alright, so talk about 4a, finite difference part. So problem is a strange one. Minus epsilon uxx plus ux is equal to 1. And x is between minus 1 and 1. And then you have, again, homogeneous Dirichlet boundary conditions. So u is equal to 0 at plus or minus 1. Okay. Now, before I talk about anything related to finite difference, so I was thinking like, well, just like problems 2 and 3, you're going to study error, and you want to have an exact solution to compare against. So I thought, okay, well, let's do that here too, compute an exact solution. But things went awry. First, look at the case of epsilon equals 0. So that first term just goes away. So then you have u dx is equal to 1. And then you have boundary conditions. So in that case, very simple ODE. What would the solution be? Or,
X or
yeah. So u of x is equal to x, what am I missing?
Plus a constant.
Yeah, plus c. Okay, okay, no problem. Then I'll just have this satisfy the boundary conditions and we'll be done. But what goes wrong when you try to apply the boundary conditions to that?
negative 1 doesn't equal 0.
Well,
No, that doesn't make sense.
well, let's plug in x equal plus or minus 1. So u of 1, which is 1 plus c, must equal 0. So what's c?
Negative 1.
Okay. Now, so the other boundary condition, u of minus 1 is minus 1 plus c, also equals 0.
C has equal 1.
Yeah, so then the whole world blows up. There's no solution. So there is no function that satisfies boundary conditions. Yeah, so that's a very excited end. I couldn't resist. Okay. So in other words, that epsilon term really needs to be there. And it makes sense because PDE, if it only a second order PDE should have 2 boundary conditions. Otherwise, first order should only have 1. So in that case, it turns out to not really be helpful. Now, can anyone think of how you go about solving that? Because in the previous problems, you had uxx equals something, or uxxx equals something. And that wasn't really a problem because you could just integrate the required number of times. But you can't really do that here. What can you do instead? This kind of equation, something like this, of this form, does come up in an undergrad class. Well, it's probably pretty obvious which undergrad class it comes up in, but however, anybody, we'll see. Well, Two of you took that class from me. So really, because x is the only independent variable, we have a second order ODE with constant coefficients since linear. How do you solve something like that? I know it's been a while.
Do you like integrate each part with respect to each boundary condition?
Well, boundary conditions really have to wait until the end.
It's like the characteristics of.
Yes, characteristic equation. What does that involve?
Doesn't it have like. No.
What? Okay.
Doesn't it have like an A and a B?
Yes.
C. There's probably C.
And where do they come from?
Is it sine and cosine stuff?
Well, that's one scenario, but
I thought it was just how it was set up. Like, you just have to observe what it looks like, and then you know there's a characteristic that comes from that form.
no, something called, okay. If AU double prime plus BU prime plus CU is equal to, well, first procedure is where it's equal to 0, which is not what we have here, but the characteristic equation is AR squared plus BR plus C is equal to 0. And you solve this quadratic equation for two roots, which I'll call R1 and R2. So these are real and unequal. Your solution has this form, a constant e to the R1x plus constant e to the R2x is your solution. Does that ring a bell?
Mm-hmm.
Okay.
The E's do.
What?
The E's do.
Okay. What happens if they are real and equal? You can't have two terms of the same form. Does anyone remember? So you would have that. But what's the other term?
Real and equal?
Yeah.
It's just a constant by itself.
No.
What if they're
One.
No.
if you get two roots that are equal,
Yeah.
then you don't have a second term, right?
Well, it can't be that term. So we need a different, slightly different function. Want to take a shot at it? Okay, so, well, that's okay. It was 2 years ago, 2.5 years ago. X e to the R1x. So that's how you distinguish. And then the last case was R1 and R2 complex. But because A, B, and C are assumed real, they have to be complex conjugates. So it's cosine and sine. It actually could be exponential. So so they had to equal like alpha plus or minus I beta. So it'd be e to the alpha x cosine beta x, and then e to the alpha x sine beta x. Okay, so those are the three possible forms. I guess I'm doing a 285 review right now. Well, why not? I do have time. Okay. And then the constants would have to be found using a boundary conditions. In the case where your right-hand side is 0, but here we have 1. There are two procedures that are taught in 285 for how you handle the case of a non-zero right side. Gold stars to anyone who remembers the name, just the name of either of those methods.
Some German
No.
Okay.
Ordinary English words.
Wait, what is it again?
There are two methods for solving an inhomogeneous ODE. So you have something non-zero on the right side. So here we're finding a solution of a homogeneous case. So there are two methods to, okay, because we're having to find, if it's non-zero here, you have to find a particular solution and add that on to this solution. So there are two methods for finding that particular solution. One of them is a method of undetermined coefficients, which involved a ton of really tedious algebra and taking law derivatives. The other is a method of variation of parameters. We're actually working out some integrals. So the first time I taught this class a couple years ago, let's go ahead and use this procedure and one of those methods, undetermined coefficients, which would probably be easier for this case, and actually work out what the exact solution is. And based on this characteristic equation, well, A would be minus epsilon, B would be 1, and C would be 0. So the roots, R1 and R2, I'll just rework those out, I don't remember what they were, but so we have minus 1 plus or minus square root of 1 minus 4 times A, which is minus epsilon, times C, which is 0, all over minus 2 epsilon. So just applying a quadratic formula. So what we end up with is minus 1 plus or minus 1 over minus 2 epsilon. So we get 0 for one root, and then 1 over epsilon for the other root. Okay. I feel like I do remember 1 over epsilon occurring in the exact solution. So that means a homogeneous solution would include a term that's a constant. But you also have, so your solution would include a constant function and e to the 1 over epsilon times x. For this problem, the value of epsilon is given. Epsilon is 10 to the minus 4. Well, that's the first case I looked at.
Okay.
Yeah. Just to see what it looked like. Okay. And so something went terribly wrong. And now what I've not done, I've not bothered to figure out a particular solution because that would take too long. But I remember doing it a couple years ago. The bottom line is, we get functions like this appearing in the solution. And there may have been something like e to the minus 1 over epsilon x also, I don't remember. I thought, okay, no problem. Let's plot the solution for x going from minus 1 to 1, see what it looks like. You can't. So you can work out the solution on paper, like I started to do here, no problem. But when you try to work with a solution in MATLAB, it cannot be done because you plug in x between minus 1 and 1, and epsilon being 10 to the minus 4, you're computing e to the roughly 10,000. I have MATLAB up, so I'm going to compute e to the 10,000. That has a problem of floating point arithmetic that would be referred to as what, Sarah?
Overflow.
Overflow. Yes. Okay.
Probably
Yeah.
got that one wrong.
I don't remember. We'll find out. Okay. All right. Well, maybe I'll give you points back then. because e to the x is a very rapidly growing function. You plug an argument as large as 10,000, that thing is way off the charts. In fact, if I evaluate e to the smaller number, like 10 cubed, also overflow. E to the 10 squared. That does not overflow. It's 10 to the 43. So, all right, so that's well under the limit, but still. Yeah, so you cannot evaluate the solution. If I do e to the minus 1 over epsilon x, what would that lead to? What? Yes, it would underflow for the same reason. So it was just impossible to plot the solution from a formula. I was like, okay, fine, now what? So really, you can't do the same kind of error analysis as any other problems, so I'm saving you that problem. Although it would have been fun to have you like go through all this and try to figure it out, and only to have a solution you can't even use. Okay, you guys would have hated me for that one. Okay, it's probably best I didn't do that. Okay, but these are things that happen. You think, oh, I'll just do this, because that's what you would normally do, and then like, oh, wait. So that's what makes this field kind of adventurous. Because things that work out on paper just fine, you try them on the computer, it's like, oh, no. Yeah, that's why I have a hint. It will be practical to compute the exact solution this time. I don't really say why. Now we really are almost out of time. But as far as solving this in MATLAB numerically, for both of these derivatives, use the appropriate center difference formula. So this part is just like problem 2, with just multiplying by minus epsilon. Because it really is the same thing, because that problem was minus uxx is equal to f. So you'll make a matrix for this, it'll be much like a matrix in problem 2. And then you'll throw in another matrix that has the same kind of situation, except using a different finite difference stencil. So this one would have 1 over 2h, and then zeros on the diagonal, 1s above, and minus 1s below. So the resulting matrix is not symmetric. And then your right-hand side will just be all 1s. So other than that, it really isn't any different from problem 2. And you can't do the error analysis because you don't have the exact solution. But what will happen is, well, it's discussed in the notes, but the solution will behave badly. But as you use a larger grid, as you increase capital N, the behavior improves. But the idea is it takes a long time. N has to get pretty large before that happens, because this solution has what kind of looks like a discontinuity. It isn't really discontinuity. It just gets incredibly steep. And then in part B, you solve the same problem with a Chebyshev spectral method, and the behavior is better. You don't have to let N go so high before you get a reasonable solution. So, because spectral methods rule. So, put that on a tombstone. Okay, so that's problem 4. Okay, yeah. Well, that's more than half a semester's work.
What time does it say on your laptop?
5:53. Oh, what? Okay. All right. Yeah. So we'll see what you guys can do over the coming week with these 4. It may take a while, but we still have a good amount of time. And then I think I'll hold off on talking about any others until some progress is made. I may cover some new stuff during part of the class, like especially on Monday, just to keep things moving along, because there is more material to cover. But yeah, let's have fun with MATLAB. Alrighty.
I think the mathematical symbol to show excitement should be an upside down exclamation point.
Okay, well, as long as it doesn't confuse any Spanish speakers, then yeah.
Or look like